Hello, algorithmicians. We're going to go through a trial exam, which, as an algorithmics teacher, I've written myself because there don't seem to be any good quality resources out there. And let me start this by saying it is really hard to write a trial exam. So some of the questions you're going to find didn't quite hit the mark or are not entirely representative of VCAR style questions. I'll try to indicate that as I go through. Nonetheless, hopefully this will give you a good opportunity to check your understanding, to identify things. You know, if you realize you've forgotten what an NP hard problem is, it'll help you see that. And even if I can't tell you on the video exactly how many marks you would have got for a particular question, I'll at least be able to tell you what you could have done to make it better. So the kinds of things we can do to guarantee the marks. Because ultimately these things are subject to the decisions of the examiners on the day. Once again, I'm not affiliated with VCAR in any way. This is just my own effort as an algorithmics teacher. So here we go. Oh, and before we get going, I'm going to be adding more exam run-throughs. Run-through, there must be a better word for that. If you hit subscribe, then you will find out when they come out. So, multiple choice, here we go. Oh, if you're doing this, by the way, and you haven't seen these questions before, make sure you pause the video. I'll try and make that obvious. And try the questions first. Now, this first one, the only one that doesn't work is B. And I don't know if this was a little bit mean. I think it is clear, though, because the clue is it's a large multinational company. So there's probably going to be more than one person with the same full name. Everything else is absolutely fine. You might be uncomfortable with D, storing an array as a value, but that's absolutely fine. In fact, in algorithmics, we've seen examples where you can even have things like an array as a key, where in Python that would come up as being not hashable. Number two, the answer here is set, because the only operations we can have with sets, well, what would they be? We could add an element to a set, we could remove an element. These would both have a set as an output, and we can also have the in, which checks to see if an element is in a set, which is either going to be yes or no. So it's definitely not a set. Number three. Go through these one by one. The minimum spanning tree, you have to have every edge, that is the minimum weight. Well, no, I mean, imagine if you had a complete graph with all edges that are the same. So let's just draw a complete graph. All of these edges have a weight of 1. The minimum spanning tree is not going to include all of them, so definitely not A. Does not contain the edge with the largest weight. Well, again, and it's helpful to do a little example, because this one will help you answer C. Well, help you see that the answer is in fact C. So here we have a graph. The minimum spanning tree is going to have to contain the edge 10 because that is a bridge. There's no way of doing a minimum spanning tree without including it. So it's not B. And the answer, hopefully we can see here, is C. If we remove a bridge, the graph is disconnected. So in the bottom one I've done here, that 10 is a bridge. I could stick another bridge in here. Let's call that one 11. That 11 is also a bridge, so the answer is C. And we know that a minimum spanning tree is not unique for a given graph. Again, looking at the example on the right, there are heaps of minimum spanning trees that I could do. Questions 4 and 5. So this is one we're going to do with the trace table. This one takes a little bit longer. I feel there's probably a few more steps than we would realistically have. So A and B, we are doing 7 and 5. A is greater than B. B equals A mod B, so that's division of 7 by 5, which is 2. A equals A minus 1, which is 6. B is less than 2, which it isn't. So we continue with that loop. B equals A mod B, which would be 0. A equals A minus 1, which is 5. B is less than 2, so we change it to 3. We do the loop again because A is greater than B. 5 divided by 3 leaves a remainder of 2. A equals A minus 1, which is 4. b is not less than 2, so we continue. A is still greater than b, so b equals 4 mod 2, which is 0. A equals a minus 1, which is 3. And b is less than 2, so we let b equal 3. Now at this point we can see that a is not greater than b, so the loop stops and we return 3 plus 3, which is 6. Okay, I had to do that twice because the first time I got an answer which wasn't there. So if you get time, these are worth going back and checking. Okie dokie, number 5. Negative edges, but no negative cycles. So I was sort of getting at something else here, but the best answer I think would be B, Bellman-Ford. This is pretty much factual recall. We know that Dijkstra can sometimes give us the right answer with negative edges, but we can't guarantee it. So Bellman-Ford is the only one which reliably finds the shortest distance using where negative edges exist. That is to say, of those options, I think Floyd-Warshall also works with negative edges but no negative cycles, but we can only choose D, and that's not an option. So there we go. Okie dokie, I think this is pretty much factual recall. Greedy design pattern means choosing the next best option at any one point without regard for the globally best solution. And that is how PRIMS works. Depth first search isn't. It kind of chooses depending on where you are. Binary search is divide and conquer, as is merge sort. Okay, so we're going to try BFS on each of these. So we start at A. We have to add all of the neighbors of A first. So the next 3 have to include B, C, D. So A, B, C, D, A, D, C, B. So straight up, we can rule out D. So let's just look at D, because it would be like A, and then B, and then E. Well, that's looking more like a depth first search, although I don't think it's that either. So now we can consider, we'll look at A. So if we did A, we would do then B, D, B. Now we should be looking at the edges for B. So the next one should be E or F. So which I think it is A, B, C, B, D, C. And then, yeah, we can do F, so doing all the edges of that one. And then we can consider all the edges of P, which is G. Okay, oh, and I've just read the question again. Haha, read the question a bunch of times. We've already identified that D is not possible, so we don't need to do this. We could go through and prove that the rest of them are correct, but there we go, done. Always read the question. I remember in my, however many years ago it was, I went to school and my maths teacher would write this when someone didn't read the question properly. This, of course, stands for read the question. Moving on. Okay, Inception. I thought that was the most perfect name ever for a recursive algorithm. Oh, Leo. Right, so we would do 5, 5. If A is less than 2, which it isn't, A is greater than B, which it isn't. So otherwise we're returning inception, A minus 1, so that's going to be 4, and then 3. When we go through again, if A is greater than B, which it is, so we do B minus 1, which is 3, 2B, which is 6. Have I read that right? To B minus 1? No, I haven't. Oh, read the question. B minus 1, so 3 minus 1, which is 2, and 6. There we go again. If A is less than 2, which it isn't, A is not greater than B. So now we're on that third statement. We do A minus 1, which is 1, B minus 2, which is 4. Now we run inception again, and we return, because A is less than 2, we return B. So this is our final call. So we ran inception 5, 5, which didn't count. That called this one, which is 1. That called this one, which is the second call. That called this one. And this last one, when we called inception 1 before, it didn't call it again, it just returned B. So the answer is 3 times. Quite easy to get that wrong, I think. Like, just you could be 1 out quite easily. Okay, questions 9 to 11. So, cannot be solved in poly time, so we know it's not that one. And verifying the solution is at least as difficult. So, we know that problems in NP are it's non-deterministic polynomial. So we know, or we're not aware that there's a polynomial solution, but we can verify them easily. So anything in NP can be verified in polynomial time. That includes NP complete. And because we're told that verifying the solution is at least as hard, so that means also cannot be done in polynomial time, we must be in NP hard. NP hard problems may not have a verification option in polynomial time. So pretty much straight definitions. The diagram we're using for this, or I think this is the best one, NP hard, NP complete. That's the most useful one, which you'll find everywhere. What does the Chinese room argument attempt to prove? Well, the Chinese room argument does not necessarily prove that computers cannot think. What it proves is that just because something looks like it's thinking doesn't mean it actually is thinking. Okay? So we've got this Chinese room situation, and the guy inside is mimicking someone who understands Chinese but doesn't actually. Now, to say that means computers can never think, that's like saying that people can never understand Chinese, and like there's a whole bunch of Chinese people who do understand Chinese. So that's not what this proves. It's about what can we know, or what does one result imply. So that means A is wrong. B, I was trying to allude to the robot response. I mean, yeah, it doesn't follow logically. And D is also the same thing. It's the systems response, kind of alluding to it, but that's not what the question's asking. And so, although the Chinese room argument doesn't explicitly reference the Turing test, we're saying, well, just because something looked like it is intelligent doesn't mean it has understanding. Number 11. So when we increase the number of dimensions in SVM, we could increase them to equal the number of data items, but then when the data is very, very far spread out, it becomes harder to draw a definitive plane which we know is correct, because we end up in every dimension there are just 2 points that we're separating, so it becomes rather arbitrary. Imagine trying to do a scatter graph that goes between, well, not scatter, trying to do a boundary between just 2 points. So, I mean, it could be, we're not going to draw that as definitively as if we had lots and lots of points. And if we increase the dimensionality, then when we look at it with reference to particular dimensions, there would only be 2 points to consider. So this gives us the risk of overfitting. Let's talk about the others. I would say it makes it more likely that a hyperplane can be found, so it's not B. I keep wondering if anyone will make this mistake. Nobody has so far. That the idea that you can only go to 3 dimensions because that's what you can draw pictures of. That's obviously not true, and you know the complexity will get much harder if we increase the dimensionality. So there we go. Hey, the PageRank question. You can't tell because I've recorded and deleted this. This is now the 3rd time I've done this because mistakes I made the first 2 times. I forgot the damping factor, which is just inexcusable, but also I forgot that there are 2 sync nodes. I looked at C, didn't notice D, probably because of these dodgy arrows. I used a little Python script to construct some random graphs. Yeah, that's the way it goes. So each time we do this, we've got 2 sync nodes to consider. After initialization, so they are all 0.2, 0.2, 0.2, as in 1 divided by 5. So first iteration, and we're only going to have to do this for all of them once, and then we're going to do it just once on the next one. So we have 0.3 divided by 5 plus 0.7. And by the way, I think the formula should be given to you. I just forgot to include it on the front. Well, they're quite intuitive. Well, I'm going to put C and D first because all of them have this one. So we've got 0.2 divided by 5 for C and 0.2 divided by 5 for D. So those are my two distinct nodes. Now A has no further inbound links, so we calculate that. We have 0.116. 0.116. Now let's look at B. B has all the same things from C and D. I'll just put a little C there and D there. B has inbound links just from A, which is 0.2 divided by 3, the number of outbound links from A. That is it, giving us an answer of 0.1347. That's probably enough decimal places because if we look at the answers, they're all quite far apart. Okay, now for C, we still include the incoming link C from itself. C also has links from B, so that's 0.2 divided by 3. It's got one from E, so that's 0.2 just divided by 1. And it's got A, so 0.2 divided by 3. Let's check that. So we've got, well, we can say we've got A, we've got B, and we've got E. So yeah, C is linked to from all the normal ones, both the sync nodes, and that gives us 0.3493. I forgot to change that. That should say C there. Alrighty, now let's get rid of all that, and we will do the rank of D. Again, you might be thinking this is possibly more than you'd expect in a multiple choice. Yeah, you might be right. Who knows? Right, we've got A, which goes 0.2 divided by 3. We have B, so that is 0.2 divided by 3. That's in each case the number of outbound. We've got C and D, and E does not link, which equals 0.2093. And finally, for E, so there you go. So for E, E is linked to not from A, it's linked to from B, which has 0.2 divided by 3. It's not linked to from anywhere else. 0.1627. Okay, now I just check that these do in fact add up to 1-ish. Fingers crossed. I'm going to be very sad if I have to do all this again. Right, we're now going into the second iteration. We're after C. So 0. Yeah, we have to get rid of this, don't we? So C has inbound links. We can start this again from A, so 0.116 divided by 3. From B, 0.1347 divided by 3. From itself, so 0.3493 divided by 5. From D, 0.2093 divided by 5. I should be drawn like that's misleading. And then from E, 0.1627 divided by 1, which had better give us the answer I'm expecting. It gives me, on my calculator with my dodgy rounding, it's given me 0.311, which is closest to A. I know A was the right answer. It could turn out I made a mistake somewhere along the way, but, you know, I mean, well, and the answers are, the whole method's correct. There'll just be some mistake there. Hopefully not. Right, moving on. Okay, Turing machine question. Next time I'll do one that's less complicated and with nicer diagrams, but this one just kind of got out of hand. B1, B1, 0, 0. And we are starting here, and we are in Q1. Okay, we're blank. We change it to a 0. I'm going to do this the other way around so I can work down the page. So we're in Q1. We change it to a 0. and we move to the right. We see a 1, that changes to a 0. We move to the right, and we are in Q2. The blank becomes a 1. We move to the right. We're now in Q3. The 1 becomes a 0. We stay in Q3. We move to the right. 0 becomes a 0, and we move to the right. And we are in a halting stage. How many zeros do we have? 1, 2, 3, 4, 5. Okay, that only took me 2 goes. 5 is an option down there. All right. Some nice, happy factual recall. Temperature does not stay constant. Controls the probability. That is probably correct. Let's just check through. This one increases to explore more states. No, we know the temperature goes down and sets the number of iterations, has no effect. That sounds there's nothing to do with it, so we're happy with an answer of B. Computing may be able to help us. Which of the problems will be unaffected? So even if we have the most amazing supercomputer ever, we can never solve the halting problem. All the others are limited by time, the fact that they are intractable. So we have the halting problem. Number 16. Let's read through these. Backtracking compared to brute force. Backtracking could take more time if the proving process is overly complicated. Well, that sounds possible. Unlikely, but let's go. Backtracking will always be at least slightly faster than brute force. Well, no, because if you explore if you end up not having to backtrack, again, it's unlikely, it seems in real situations, but it could be that backtracking is just as bad. So it's not B. Backtracking will take less time. So you see we've got the same problem, same thing here. A problem in P or NP. Well, that's kind of part B repeated again. The fact that it's in P or NP is irrelevant. So the answer is A. Now, yeah, it would be, I suspect, quite hard to design a backtracking algorithm where the pruning process was so complicated that it foregoes any benefit from not exploring the entire solution space. But technically speaking, the answer could be A. Okay, 17 is pretty much factual recall. Merge sort can run faster. No, so we know that merge sort uses more storage space, so it's definitely not B. We know that they can both run in n log n time. We know that quicksort can be a nightmare if we end up with like reverse sorted data. So A seems feasible. Merge sort and quicksort do not have the same worst case runtime, so C is incorrect. And merge sort doesn't always run faster, so really we're looking between A and D. It runs faster. I mean, as long as it would run the same if the data was completely random and quicksort partitioned into equal amounts every time. So the answer is A. Just gonna check my notes. Yeah, that's good. That's what I got last time. Okay, number 18, which does not have overlapping some problems. Well, the clue here, I mean, if you know that merge sort is divide and conquer, well, that doesn't sound much like dynamic programming, so we can jump straight to C. But let's look at the others. The Fibonacci number is the classic problem for dynamic programming, so it's not A. Shortest path in the graph, so that would kind of be overlapping, we could say, because we're using the previous information. Zero knapsack problem, again, is a classic, so the answer would be C. Moving on, last couple. So backpropagation, hopefully this is just a factual recall. Backpropagation is neural networks, nothing else. Backtracking in Dijkstra is, things sound like that, but backpropagation is a specific term for neural networks. Okay, which of these problems are in NP and not in P? The decision version is in NP. However, the optimization version is not. So let's remind ourselves, things in P can be solved in polynomial time. Things in NP and things in NP can be verified in polynomial time. Thinking about that diagram I scribbled out before. Things are in NP and not in P, therefore, can be solved not in polynomial time, but can be verified quickly. So we can quickly verify the decision version, like can you find a path between all the nodes? The optimization one we can't because we have to find all of them again. The 0-1 knapsack problem is a tricky one because with the dynamic programming, we refer to it as, it feels like it's in polytime. It's actually pseudo-polynomial time for reasons which I think are probably beyond the algorithmics course. It's one of those things I thought of making a video about, but the explanations, every time I do it, I think, man, this is harder than it seems reasonable. So so 0-1 is not in P. It is in NP. It's actually NP complete because it's the equivalent of the subset items, and we can verify it in poly time. So that one is in NP, and the graph coding problem decision version, very similar to the TSP decision version, we would include that. So there are 3 problems. Okay, that's it for the multiple choice. I don't know, is that easy or hard? I mean, obviously that the PageRank thing took a lot longer. I don't think there are any super tricky problems there. I reckon that question 20, the knapsack problem, will have upset some people though. If you're asking yourself, did my performance here represent my performance on the actual paper? I'd say this was slightly easier, but you know what? Too bad. Let's get into the short answer questions. Just a reminder, I will, if you're working through this for the first time, pause and then work through. I'm just going to show the solutions and I might talk through some of the mistakes from the trial exams that my students have sent me so you get an idea of what to watch out for. So here we go for the first one. And this was reflecting something in a previous VCAR paper where a lot of students, according to the report, didn't define what a graph was. So we want to make sure that we define what a graph is, and we want to make sure with connected we don't confuse that with complete. So we're not saying that an edge exists between every pair of nodes, we just want to say there is a path between every pair of nodes. Now for that second question, I've made another video on the ADT combinations. So this is done, I think it's rare for people to get full marks on this, the ones I've seen, because you either, like one of the common mistakes is to try and put a ADT inside another ADT, whereas as you can see here, what I've said is you've got one dictionary which is used to look up the author. Yeah, I don't know why that doesn't show nicely. So one dictionary will return the information on a book, then another dictionary will return the list of ISBNs corresponding to a particular author name. And now the justification here, I've tried to do it in terms of, I've mentioned things like big O of 1, or you could say constant time. So we'd say if I want to just look up the ISBN, that's constant time. And then to look up all the books of a particular author, that's constant time times 2, which is still constant time because we would use the second dictionary to look up all the ISBNs and then look up each ISBN in the other one. So obviously that increases with the number of books for the particular author, but we're imagining that is not going to get significantly larger. Now, when dealing with signatures, one of the common mistakes is to use non-native types. So we do not want to see author or ISBN or anything. You can annotate the native things, and when I say native primitive, that includes ADTs, right? But what we don't want to see is the real life words. So adding a new book. So we had to have the 2 dictionaries, and I've mentioned down here, so we put in brackets what these things correspond to, because it can just help people to see. Author name, title, cat, ISBN, add into these two dictionaries. That should be, I mean, it seems to come up every time once, so just do it. Nobody seems to use signatures. People are always going, oh, what's the point? Well, just go with it. Those first two questions, I think, were quite representative of the first two questions you might get in a VCAR paper. In fact, some people will look through this going, oh, you just copied the VCAR paper and changed the words, which I've tried not to. But, I've just got the imagination of one person, unfortunately. Alrighty, make sure you've paused and read this. And I will show you what we were after. Again, the map here is awful. I mean, the whole thing, if I had any pride in my work, I would have done LaTeX like the old days. But right here is my suggested solution. So for each starting point, find all possible paths using DFS. So notice I've been quite specific about finding all combinations. I think a few people said just find all the combinations and choose the ones where the maximum time is not exceeded. Yeah, maybe you might get away with that. So if I was guessing what key points we'd be looking for in a question like this, there's some description of how we would choose the possible solutions, how we would prune them in some respects. So maybe we're sort of alluding to backtracking here, where we stop when the maximum time is exceeded, and how do we choose the best one. State the design pattern you have used. Well, I used either brute force or backtracking. Okay. Describe an algorithm to quickly come up with a feasible plan. So whenever it's a quickly come up with a feasible plan, I would start thinking about your greedy algorithm, because that's pretty quick. So start at a random node. Always so we've said how we're going to start. We've said how we're going to make the decision. So you could have said choose the nearest node, or I think it would be better if we worked out for each node the time taken to get there and mine the minerals, and then the return of that, and choose the one with the highest return to total time taken ratio, and then continue until time used up, because I don't think we had to go back to the start. No, we didn't. Okay, let's go back to this one. Hopefully, right, proof by induction. Okay, so with our proof by induction, we're always like the base case, and I'll sort of scribble through this. My handwriting's very good on my notepad here, so I'll show you my work solution, but I'll take you through the thought process. So the base case is going to be a tree with at least two nodes. So this one is the only possible tree, and both of these have a degree of 1. Okay, I'll just say again, what I'm writing now is not sufficient explanation. I'm just showing you, and I'll show you my full answer. And then we'll say, assume that k nodes has at least 2 degree 1. So we're going to consider when we add one node. So there's two different. Let's imagine our graph. Okay, this is me explaining my solution. Okay, and we've got these 2 nodes here. Actually, don't like that. I'm just going to add one there and one there. So each time I add a node, there are 2 options. I can either add it here, in which case I've removed one of the degree 1 nodes, but I've added another one, so there are still 2, or I can add it here, in which case I have increased the number of degree 1 nodes. We would point out that we can only add one edge when we're doing this. I think this is something that was missed in some of the solutions I saw. When we add the node, it's assumed we can only add one edge, because we know that if we increase the number of edges beyond, I mean, it's a tree always has n minus 1 edges for n vertices, so if we were to add more than one, we would not have a tree anymore. So something to that effect. And so we can see however we add the node to an existing tree, it's always going to have at least 2 nodes with at least degree 1. So let's just talk through the solution. And you can do little diagrams here to just seal the deal. So that's our 2 nodes, 1 edge, both the leaves. We've got our inductive assumption. I mean, hopefully we can get same thing if you're doing specialist maths. Like you should be able to get the easy marks by proving the base case and make an assumption. So tree must have had a node added to a smaller tree. Now, arguably, we should prove that because we could talk about the number of edges, and we could say, well, when we added that node, we would have added one edge. So let's just work backwards. We would still have a tree. I think you get away with it though. So only add one edge per node. That's the thing I've been talking about. And then we've got here the two cases which I did a little picture for, and then some concluding statement. Now, is this representative? I think it's on the simple side. They do tend to be graph theory type questions, but it's important that you're aware of the difference between weak induction and strong induction, because I think most of the questions tend to be strong induction, which is where we, rather than moving from one case to the next case, we would say that all graphs of less than or equal to k are fulfill whichever theory we're talking about. So I've made a video on that, which you can watch, obviously enough. Okay, next one. If you looked at the exam paper I looked at, this feels an awful lot like the Oriento question in, I think, 2024. So, and again, sorry about the rubbish diagram. I was just being lazy. Fantastic game. Hopefully that makes up for my mild copyright infringement. So, the state graph would be, so make sure you pause, try it. I'm just going to show you, talk through the solution now. I think people generally found these fairly straightforward, but make sure you've got these points that unweighted, since each move costs the same, and undirected because you can move in either direction. And I've put some other stuff there which is possibly not important, but yeah, so those first two lines are really what you need. Okay, how could we quickly find a solution? Well, whenever we have unweighted graphs and we're trying to quickly find something, you're hopefully thinking BFS because it's unweighted or all weights the same. We sort of move out in waves. So we've got our initial state, which leads to a whole bunch of other states. So that one leads to those, which leads to these, and so on. And we start here and we move out in waves, and we will find the first one. I suppose that it should say in the least possible moves. That would make this question a little bit better. Arguably, DFS could actually find solution just as quickly if they are random. So there you go. Just me being honest. That's where it's not a perfect question. And marks are probably only really two. And for C, got to pause it, never mind. So now we are changing the weights of the edges. And I mean, it says solution can always be found if one exists. Again, I haven't worded the question properly. It should have been, how can the shortest solution be found if one exists? And the thing we would be looking at is extra. I feel I'm skimming over that question. That's just a reflection of my disappointment in it. So, although it does reflect the 2024 Oriento question, it's not written properly, and it's not very interesting because it's almost exactly the same. Okay, this one I really liked because it took me a while to find a tricky master theorem type question. So we want to work out how much does this divide. So this is a divide and conquer. We can sort of tell because it's recursive and we've got some dividing things. So what this does is find the 2/3 point of an array. So I'll illustrate what this does and then I'll explain. So we have our array to sort. It takes the first 2/3 and then the second 2/3, and then the first 2/3 again. And let's just work through why that works through. So we've got low and high. I probably should have explained that it starts with low being the start and high being the end. So if we will go consider the sort of base case of the recursive thing later. So n, let's look at these ones here. N is the number of items. So I minus low plus 1. And then we find the 2/3 value along. So let's say n was equal to 9, m would be 6. So then we run these algorithms 3 times. We go from the bottom, from low, to low plus the 2/3 point minus 1, for that continuity correction. Then we do it from the top 2/3 down, so that's like this bit, that's the top 2/3, up to the top, and then we do the bottom 2/3 again. Okay, the base case, we're saying if we only have 2 or fewer items, then that's the recursive bit where we swap them if they're not in order, and then the whole sorting thing reprocesses them. So each time we do this, we end up with a equals 3 because it calls 3 instances of a problem. Now, it's 2/3 of the, so if you think about the master theorem, it's like a t n over b plus n to the power of c. You'd want to say that b is 2/3. It's not 3 over 2 because we're timesing by 2/3, which means we're dividing by 3 over 2. Sneaky. And then c equals 1. Or doesn't it equal 0, constant time? Okay, then we consider a and b to the power of c. So 3, and then 3 on 2 to the power of 0. Well, that would, this on the right hand side would equal 1. Why have I written 1? I was thinking 1 because I knew it equals 1. 0. So we know 3 is greater than that, so we are dealing with case 3. So it's big O of n to the power of log 3 on 2, so let's say 1.5 a, which is 3. Right, comparing that to merge sort, well, merge sort is n log n. This is, well, 1.5, you can do it on your calculator, to the power of, like, I don't know, between 2 and 3 is, so it's slightly worse than a quadratic. Stooge sort is slightly worse than quadratic. So we would say the time complexity is worse. The way I've written it here, or the way Grok wrote it, is actually, it's not it's not making multiple copies of the algorithm like merge sort does. So we normally say that merge sort has poor space complexity. This is actually sorting in place. It's not returning stooge sort, it's just carrying it out again. So in this case, the way it's written, we would say the space complexity is better. But if I'd made that return stooge sort, then it would be worse because we're making more arrays, so it's overlapping a bit more, which is what I've written here with a justification that the way I've written is kind of wrong. Finally, if we take stooge sort to be a slightly weird variation of merge sort, we know merge sort runs in n log n time regardless, and stooge sort is kind of the same. So it doesn't look for pivots. We haven't got the problem that happens with quicksort, where if we get bad data or bad pivots, we can end up with much worse. So this would be something to the effect of, well, runs the same for any data. Yeah, not much of an explanation there. You know, if we wanted to, if you got that question, which I suspect is not perfectly written, we might say something like, well, it's not like quicksort where if we choose a bad pivot, we can end up with the data being unevenly split. So we can say it always splits the data in the same quantity. That would probably be a more full solution. Okay, question 7. Try it first. Hopefully you can see this is similar to the 0, 1 knapsack problem. Now, a couple of people said, why is it not like the coin change problem? Because it's just got that one array. So the coin change does genuinely just have one array. This one, it's kind of hidden, but the 1, 5, 8, and 9 corresponds to 1, 2, 3, and 4. So you've got to read the example there. And it's again, it might not be written perfectly, but we're saying 1 meter costs $1, 2 meter costs $5, 3 meters costs 8, and 4 costs 9. And we're trying to find the maximum way of, for example, splitting up 4. Okay, so this would be a knapsack problem, 0, 1 knapsack problem, and we would solve that, as we know, by dynamic programming. So there it is, and hopefully you have tried your pseudocode, and I will talk through my solution here. I often find it is more intuitive to use one indexing arrays, and so I have said that's what I'm doing. So we've got the algorithm, the line here, which takes the required inputs. Often, like if we're thinking through how to write pseudocode, there's going to be initialization, there's the doing stuff phase, and then there's the returning phase. So um, the dynamic programming arrays is going to go a bunch of zeros from 1 to the target plus 1. Now remember why I did that. Let's see if that makes more sense. So we'll go through it and sort of error check this as we go. So the first thing we always go through is it's like for each length. So like when we're doing the knapsack problem, we consider what if we just had that one item, and we consider what's the best thing to bring based on that weight. And then, so that's why that is our outer first loop. And then for J, between 1 and our target, so then we're considering like for each item, should I include it or not for each of my prospective target values. So first off, the possible target value needs to be greater than the length of the rod, so that's what this line here is. And if it is, then the best price for the particular value is either going to be what it was already, or it's going to be the price of the rod we're going to use minus the got entangled. The price of the one we're going to use plus the price, which are the best ones so far, of the one of the target weight where you've taken away the amount involved. Now, I feel like it's probably worth actually trying this out. So let's run a target of 8, and we're going to do it with 1, 5, 8, 9. Hopefully that is valuable. So we will have an array of a bunch of zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is my DP array. This is prices here. Then we're first going to consider 1. So we'll just put the indices here. 1, 2, 3, 4, 5, 6, 7, 8. So you can see that's why it made sense to have the array of 1, like including the extra 1, although the 1 indexing thing seems slightly wrong. I might have to go back and change that. But we're going to have just item number 1 with 0. We can't include it. With 1, we can, and it's worth 1. And then that was the only option we've got. So the rest of these are just going to be worth 1. Well, this could end up being a heavy going. Now we're going to have 1 and 5. So that 5 is worth 2. So we would only consider it when we get to here. So dp of 2 is going to be the maximum of dp2, which is currently 1, or prices of 2, which is 5, plus dp of 2 minus 2 which was the weight minus 1. I must have had something in mind there with, I think it did work because I remember doing this on Python. That's why I've got the little print statement down here. I think this should probably be 0. I think that's probably where that's gone wrong. Anyway, so it's not actually one indexing arrays. We're just sort of thinking about one indexing arrays, I think. Okay. Then for 3, well, the maximum for that is going to be 5 plus the 3 minus the 2, which is the 1 here. So it's going to be 6. So what we're saying for this one, if we had a length of 3 and we had the first two options, 1 and 5, we would cut them into lengths of 1 and 2, corresponding to $1 and $5, which would give us a total value of 6. And then the rest, we've used them all up. So it's going to be, hang on, no, that's not right. So in fact, this isn't really the 0, 1 knapsack problem because we can split this into, we can use things over and over. Go back and change that. Well, I'll add a comment maybe. Okay, so does that mean we've got to go back and change all of this? I wonder. So let's say we're doing for 4. So we could have included the 2, which would be worth 5, plus the 5 there, which is 10. So I think that works. Then when we get to 5, we would have included the 2, which is worth 5, which takes us down to 3, plus the 6, which takes us to 11. Yeah, so I think this actually works. Well, that's a relief at least. Yeah, it's funny when you start talking through a problem and then you find that, oh, probably shouldn't have started making this video. Oh well, whatever. So this bit is the bit that's really worth learning, and then you're returning the final step. So this bit is very, very common when you're doing your dynamic programming, if it's anything like knapsack or whatever. Now, just another note on this, if you're, in terms of exam strategy, it's quite easy to get the first few marks for doing things like, well, initialize it correctly. Like to write it in general, I would say with algorithmics, it's quite easy to do things like 60 to 80% good. And then you're going to spend, after you've got time, if you have time, to go back and check that all the indexing lines up and all that sort of thing. Okay, next question. Here we go. Now, this takes quite a bit of time to read through. Let's just try and pick through this. So we take a list of marbles and a list of bucket. And for each marble, if the marble is bigger than the next one, then we switch them. And we then check to see if the marble is bigger than the next one, then it is not sorted. So we do a kind of sort of crude sorting algorithm here. And then for each marble, we put it in one of these 5 buckets. So we sort the marbles in order, and then we put them into a bucket. And then the final thing, what does it do? For each bucket, it counts the number of marbles and records the maximum, the bucket with the maximum number of marbles. And then we go through this final bit here for each marble, each pair of marbles in the maximum bucket. If the weight is same and the marble itself is not the same, so we're making sure that we don't, comparing the same marble and say, oh, it's the same weight. Then we add the weight of that marble to the result, and the final thing we return is the array of marbles, the array of weights where the marble has the same weight. No, the array of weights where at least 2 marbles have that weight. Okay, now I think just looking through this, do I have result? I've got a feeling I didn't. Oh no, I did. I've initialized result. Oh, and it's not an array, it's a set. Okay, so that is pretty much an explanation of what this does. Let's see what we had for the thing. You can see my time complexity thing there. So for A, check your working, and then for B, we've said what will lead to the worst case. Well, that sorting algorithm we've seen is not one that's covered in the course, but if you have to sort the algorithm, if you have to sort a list of marbles from reverse order, it's going to do an awful lot of switching because each time it runs through, it switches the marbles. It has to move each marble up one step, one by one. So it's going to take a very long time. And then the worst case scenario is if all the marbles end up in the same bucket for the second part. So, I mean, I tried to write this to make it interesting. It's ridiculously contrived. I mean, who cares so much about marbles? But I quite like this one. And then we've completed a time complexity analysis. And it's always okay to just annotate the code on this unless you're explicitly told not to. So we go through n times this first part, and each time we're looking at every single marble, so that's why the first part is n squared. This bit here, where we're putting the marbles into buckets, we're doing that once per marble, so that's big O of n. This part here, you can see, is all big O of n, because we're doing it just for each marble, plus a little bit of something for each bucket. And then this last one here is a very familiar double nested loop, so it's going to be n squared. I've used n rather than v for the number of marbles. And then you can see I've added it all together. Don't just say, oh, it's big O of n squared. Just sort of explain the reasoning as to why the time complexity is, in fact, n squared. Okie dokie. Right, now we're on to, and I try to replicate the feeling that the questions towards the end tend to be a little bit more Unit 4, like Outcome 3 thinking, philosophy type questions. That's what I was aiming for. Although this one starts technical. So, as with every single modeling question, take an aspect of real life and say how it corresponds to the aspect of the model. So we would say each student is a node. If a student A has chosen student B, then there is a link from A to B. Now the limitation, I had to put this in here, there was a question a little while ago where the damping factor, I think it was to do with the fairground, did make sense. In this case, the damping factor doesn't really make sense because we're just saying we nominate 5 students who we want to be with. There's no real random choosing in that process. Obviously, when we then use that information, you're not going to be in the same class with all those people, and there'll be some other people there as well. But that's not really included in this process. So that will be the limitation. We say the damping factor doesn't really work, which you can see is explained there. Oh, okay, still into the technical things. I must have, I was thinking of something else or just forgotten. Who knows? This is quite typical of algo questions, especially of recent years, where they give you a helper function. And there was a question, actually, it was quite similar to this, where we had to, the PageRank algorithm was given to us and we had to run it a number of times. I want to say 2023. So I will just show you my answer to this and talk through how it works. So we've got the captains. We're trying to get 3 captains. So we've got an empty list of captains, and for each of those captains, first off, we're going to do the find the ranks with PageRank, and I've actually made another algorithm for PageRank down here, which I'll explain. So we find all the ranks using PageRank, take the student with the highest rank, add the student to captains, remove the student from G, and then we're going to do that 3 times. Now, how does PageRank itself work? This one down here. First off, we initialize it. Again, we're doing initialize, run, return. Initialize it, so there's a dictionary. Each node, probably should say that as a key. As the key, the rank is the 1 divided by the number of nodes as the value. Now we've got different options for when do we know when to stop? And we can just repeat it like 1,000 times. It's a bit crude, and you might decide, well, I'm just going to repeat it until for every single node in the dictionary, they are within like 0.00001 of each other. In other words, we've achieved convergence. And then we return the rank. So I've actually made my own helper function for my overall function here. And you could have written that as one big function, but I feel like you could have stuck that in the for loop, I suppose. This just seemed neater. That's nice to know it's an option. Okay, I quite like this question. It's very representative because, well, it was almost exactly the same as the previous one. Right, this is the Unit 4 Outcomes 3 type thing. So let's imagine, we're in a school and teachers know all sorts of things, physical description, grades, all that sort of thing. And we know who's previously been chosen as popular. And we make a neural network to work out which kids are going to be popular in the future. Right, the ethical problems the top three we're interested in are bias, transparency, and accountability. Accountability says who should be responsible when decisions are made, and I find that's often a hard one to wedge into essays. So the top two are transparency and bias. Transparency is often quite an easy one. So when we're talking about neural networks, we'd say, well, I need to be able to explain to kids how they were chosen. And the neural network doesn't let us do that. So that would be a problem. That's usually quite an easy one to fit in. Bias, look, in reality, we can often just kind of say bias and get the marks. But if we want to be better than that, bias is it's not just like, oh, well, it might always have chosen girls or it might not like particular kinds of people. So we've got this casual idea of bias like discrimination on protected traits, but bias is a bit more sophisticated than that in an algorithmic sense. So bias is where we train our neural network on a particular set of data, and then patterns in that data are carried forward to new data which is not represented by the old data. I mean, if it carried forward things which are represented, that's the whole point. So the example I'm always thinking of is car insurance. Car insurance algorithms bias against young males because they're more likely to have accidents. Well, yeah, that's why their insurance is more expensive because they're still more likely to have more accidents. That is the system working. However, if something suddenly changed and we suddenly said, I don't know, I can't think of something. Something happened which meant that young men are no longer likely to have accidents. Perhaps there was a restriction that meant they can't drive at night or with peers in their car. That's supposed to be a risk factor. Then the neural network would fail because the actual risk would have gone down, but it's still based on data where the risk is very high. So in this case, if we're talking about bias, we want to say like there'd be some kind of social change that meant suddenly certain kinds of kids were more popular, but that's not reflected in the previous training data. That's how you get a killer answer on bias, in my view. And I've put that here. Also, I've put privacy. We haven't collected data for that approach. It's a bit risky. Like sometimes people have got away with it in exams. But yeah, I don't really like it. It's often mixed up with transparency. So people will say, oh, well, you're not being transparent because you're collecting that data for the wrong reason. Like, well, yeah, that is an issue, but it's not what we mean by transparency. So watch out for that one. That's quite a common pitfall. Okay, this one is straight out of the study design, factual recall. There are a few different options. I'd say my favorite ones are better understanding of the brain, huge increase in processing power, huge increase in availability of data. Some people say things like, well, we understood more about neural networks, which meant that we got better at neural network, or artificial intelligence, more people were researching it, so that meant it was developed more. That's a little bit circular, so you might get away with it, but you can see here, these are my favorite answers for that. In general, if we can avoid circular answers, making sure you've said something new, and also make sure your answers don't repeat each other. Whenever it's like list three factors, people often kind of list the first factor on the third one, but with the words changed ever so slightly. Another one, whereas I haven't been giving you much time to pause, but hopefully you are pausing and trying these things out. We would first, it said define strong and weak AI. It's always a good idea, even if it doesn't explicitly say that, to define your terms. So whether that is defining problem complexity classes, conceptions of AI, or whatever. Now, we know that weak, sorry, support vector machines are always weak AI. They only work for that very specific case. A neural network, in theory, could be strong AI, like it could adapt to different problems. ChatGPT is not strong AI. Like it feels like it, but it is not. It's just a pattern matching thing. So um, here is what we could have put. We've defined strong AI, adapts to solving new problems. I always avoid the idea that it's truly conscious or has truly semantic understanding, because how would we ever know? It doesn't mean it can't happen, but yeah, and we define weak AIs, specific problems within certain parameters. And look, it's possible that a neural network could adapt to new problems, and look, kind of possible that neural networks could eventually have semantic understanding, although we know from the Chinese room argument we would never know whether or not that is the case. Okay, the next one. I think this was taken from a sack I did. I'm probably being a little bit casual and hand wavy in my proof over this one, but it's the halting problem and undecidability. The idea is that when a system of well, incompleteness problem isn't really in the stage of design, but it says that when we have a system of arithmetic that is sufficiently complicated, they are going to exist valid statements that can't be proven either way. And it gives us a sense of unpredictability. So there are always going to be questions that we can't answer because of the halting problem and the results of that whole encoding problem project. So that's what we were getting at here. Some people try to answer in overly specific terms, say, well, you never know what those crafty hackers can come up with. Yeah, true, but not really what we're talking about. So limitations with knowing what programs can do, and we never know if it's going to behave in the way we expect it to. Because when you write, I mean, it's often hard to think, well, how do people hack things? It must be easy enough to write something that doesn't have all these loopholes. You hear about bugs and things. You think, are programmers really that lazy? Well, no, it really is impossible to avoid all these problems, or at least to know that you've avoided all these problems. And finally, the essay problem. We haven't seen that many of these. It's only been um, 23 times 2 because it was a sample paper, and 24. So there's only 3 of these long extended essay questions, but we do need to try and get used to them. I'll say at the outset, if you did try this or if you're about to try it, it's not as difficult as the ones you'll get in the exams. It doesn't go into enough depth. So like, it doesn't give you the opportunity to go into enough depth. But have a go, and then I will show you some of the things I came up with. So here we go, not enough training data, or we could say it's not for enough different, wide enough variety of contexts and scenarios. Um, some people talked about the inputs and the sensors. That's where this question isn't perfect. So try and choose things that are relevant to algorithmics, but if you got this question, it might be all right. We talked about the training data not being diverse. Different scenarios have different requirements. On that subject, somebody put, well, if it's being trained on real life drivers, it could be that you've got some really aggressive drivers making mistakes. And so the AI will include those little mistakes, which I thought was interesting. Yeah, I'm not sure. I think it's okay. Somebody talked about the speed problems, and that's actually correct. It's not someone that I'd thought about. That it's got to make quick decisions. I mean, like when you're looking on Google Maps and you want an answer quickly, it takes a little bit longer. Imagine if you're actually doing self-driving. You have to have incredible processing power. We've gone back to this idea of the halting problem. I must have been thinking about that a lot when I was writing this, that we don't know how the system will behave under all situations. And also, I mean, that's related to the transparency of the neural network. We don't really know how it works. And the bias, again, I've been banging on about this a lot lately. It's For example, what if driving habits change? Let's say after COVID, everyone got more aggressive or less aggressive, or maybe suddenly we had a demographic change, which meant pedestrians behaved in a different way. These may change, but the car won't instantly adapt. Then the ethical issues, I tried to get at something here because I remember hearing that you can either, I think it was in a movie, you can set your car to protect the driver or to protect the pedestrians. And if you do that, well, who's accountable for it? So wedge some accountability into there. We've got the transparency pretty much mentioned, and the ethical standards also may change over time. So we could try and have some AI which would explain its actions, which would also need training data to explain the actions, and collect data from more diverse conditions. I suppose some of the other problems are obvious, how you would solve them. Get better processing power, better inputs if you had gone down that route. Okay, hopefully that's useful. Feel free to put in the comments if there's any mistakes I've made, and I'm probably going to make some, or I'll hopefully add in some videos which will give you more practice at some of these concepts. And also, if you do subscribe, I'll be rattling out some more of these, hopefully the 2023 papers soon enough, and also the 2025 paper when it comes out. Don't know if you'll be watching this much later or... Yeah, okay, hopefully this is helpful. Bye.